Today, we're going to start talking about Laplace transforms. And the basic idea of a Laplace transform is to change the language in which you're doing a problem. So, an analogy, the Paris office of your New York City-based company sends you a message about a problem they need you to solve. The message is in French. How do you proceed? And here we're assuming you don't speak French. So what you're going to do is take the problem in French, translate it to a problem in English, which you can understand and solve. You write your solution down in English, and then you translate it back to French to send to your Paris office. And the reason you do this is for you, the problem is much easier to solve in English than it is in French. And that's the basic idea of the Laplace transform. French is going to be functions of t, and English is going to be functions of a new variable s. So we're going to translate functions of a variable t to functions of a variable s, and we're going to find that the problems are easier to solve in this new language. Our translation software is the Laplace transform. So let's see what that is. The Laplace transform of a function of t will equal cap f of s, and that's the notation. Little f of t is transformed to cap f of s by this integral, the integral from 0 to infinity of f of t e to the minus st dt. Cap f of s is called the Laplace transform of little f of t. So before we do anything else, let's do an example. Let's take an easy example. F of t is the constant function 1. So the Laplace transform of 1 is going to be f of t, which is 1, e to the minus st dt. Now this is an improper integral, and you should recall from calculus that this integral is actually the limit as k goes to infinity of the definite integral between 0 and k, e to the minus st dt. And this is not hard to integrate. E to the minus st, antiderivative, is e to the minus st over minus s. Okay, and we're going to take the limit as k goes to infinity of that. Okay, now we evaluated at the two limits, and at k we get minus e to the minus sk over s, and at 0 we get 1 over minus s, and since it's subtracted, 1 plus s. Now, key idea here is this term, e to the minus sk, goes to 0 when k goes to infinity as long as s is positive. Okay, so this limit is 0 for s greater than 0, which means this term vanishes, and our Laplace transform is actually just 1 over s, but for s greater than 0. Okay, and this happens with some frequency. You get a Laplace transform for some value of s bigger than something else. Okay, so example number 2, let's Laplace transform e to the at. So again, it is the integral from 0 to infinity of e to the at times e to the minus st dt, limit k goes to infinity of, and now I'm going to combine these two, and you're going to see that I actually like this minus out in front. So I'm going to write this as e to the minus s minus a t. So what you've got here when you multiply this out is e to the st times e to the at, which is what I've got right here. And now when we integrate this, this is just what we did before. Finding the antiderivative is going to be e to the minus s minus at over minus s minus a. Same idea as we had previously. Between 0 and k, lim k goes to infinity. we just evaluate at the various limits. We get this expression plus 1 over s minus a, which is this thing at 0, which is 0 over minus s minus a, and since it's the bottom limit, you subtract it. And the same idea here, as long as s minus a is positive, this limit when k goes to infinity is going to be 0. So for s bigger than a, this term goes away, and all we get is that the Laplace transform of e to the at is 1 over s minus a for s greater than a. Now, there are some important properties that our operator has, and probably the most important is that the Laplace transform is a linear operator. Just like a whole lot of things in our course have been linear operators, so is the Laplace transform. And the basic idea here is that if you Laplace transform a times f of t plus b times g of t, it's a times the Laplace transform of f of t plus b times the Laplace transform of g of t. And the reason this is true is you just write this down, and this thing goes into the integral. And now all we use are properties of integrals, which is you can multiply this thing out, you can factor constants out, and you can break up sums of functions as integrals of the sums. So what happens here is we get a f of t e to the minus st plus b g of t e to the minus st dt, both from 0 to infinity, standard properties of integrals. And what we can see here is a Laplace transform of f plus b Laplace transform of g. And that is why we have linearity. And that's going to be important because it's going to allow us to take complex expressions and write transforms of simpler expressions. So one of the things we want to do, thinking about this now as we're moving from a T language to an S language, is want to build a dictionary. Okay, what do words in T translate to in S? So here are things that we already know. 1 in T language is 1 over S in S language. E to the AT in T language is 1 over S minus A in A language. And we know that if we take a linear combination of things in T language, we get that same linear combination of their translations in S language. Now, before we go any farther, we ought to ask the question, what things in T language actually translate? Because not everything does. Okay, we need to do this integral for a translation to exist, and this integral may not exist for a variety of reasons. Okay, this is an improper integral. One of the things that you may recall from calculus is an integral from 0 to infinity is not going to exist or converge as the language went unless the integrand goes to 0 as t goes to infinity, and that gives us sort of our first condition. This limit cannot be anything besides 0, and if the limit is not 0, the transform won't exist. So we developed the following definition. F of t is exponentially bounded if there is a real number s, so that this limit is 0. Okay, this is exactly the thing in the integral that we need to go to 0. We're saying f of t is exponentially bounded if there is some real number s for which this limit will go to 0. And if you think about it, if it goes to 0 for that s, it's going to go to 0 for any bigger s's, because the bigger s is, the more rapidly e to the minus st is going to go to 0. Okay, most functions we encounter are exponentially bounded. Okay, and obviously 1 was exponentially bounded, and e to the at was exponentially bounded because we could do the integrals. One function that is not exponentially bounded is e to the t squared. And the way to see this is if I'm looking at the lim as t goes to infinity of e to the t squared times e to the minus st, I can factor a t out, and I get lim as t goes to infinity of e to the t times t minus s. Now, t is going to infinity, s is not. Eventually, t gets bigger than s. This thing gets positive, so t times this goes to plus infinity, and that means that this limit does not exist. It's in fact plus infinity, and it doesn't exist no matter what you choose as s. Okay. So to fail to be exponentially bounded, f of t needs to go to infinity faster than e to the st does for every real t, which is why e to the t squared was not exponentially bounded. Fortunately for us, almost every function that we will encounter is exponentially bounded. How might f of t fail to have a transform otherwise? Well, if you remember when we were looking at integrals in calculus, f of t might have discontinuities that integration can't handle. Okay, and there were, among other things, infinite discontinuities where you ran into trouble. Okay, now what I want you to recall from calculus is that removable discontinuities and jump discontinuities don't cause problems when you're integrating. And a removable discontinuity looks like this. It's a nice continuous function, except right here there's a hole. Okay, there might be a function definition here that's like here, or there might be no function definition, but that's what's called a removable discontinuity. You put a little point in here and you're fine. Now, the other type of just discontinuity we can handle is what's called a jump discontinuity. Okay, come in this direction, it looks nice and continuous, but when you get here, there's a hole. Come in this direction, it looks nice and continuous. When you come here, it's a hole. The two of them don't match up. And the function value at that point might exist or might be this, that, or whatever. But the idea is you come in one direction, it looks continuous, except it stops. You come in the other direction, it looks continuous, except it stops, and the two don't match. That's what's called the jump discontinuity. Now, both of these two, if you run into them when you're doing definite integration, you're just fine. You break the integral at these 2 points and do this integration, then that integration, do this integration, then that integration. Now, functions that we can deal with are functions where these are the only things that are happening. So we're going to say f of t is piecewise continuous if on any finite interval it has only finitely many discontinuities. We can't handle infinitely many of these things in a finite interval, and every discontinuity is either removable or jump. So that's what piecewise continuous means. On any finite interval, there are finitely many discontinuities, and every one of them is either jump or removable. And now the theorem is that if f of t is exponentially bounded and it's piecewise continuous, then the Laplace transform exists for s bigger than a for some real a. Okay? So if we've got an exponentially bounded piecewise continuous function, we can take the Laplace transform. And fortunately for us, most functions are that we care about. Let's look at another example, this one where we have a discontinuous function, ua of t, which is called the unit step function. The idea is that the function is 0 when t is less than a, and it jumps to the value 1 when t is bigger than or equal to a. And the assumption here is that a is some number bigger than or equal to 0. Okay, so let's calculate the Laplace transform. Laplace transform of ua of t is the integral from 0 to infinity of ua of t e to the minus st dt. And now let's remember that our function is 0 when t is less than a and 1 when t is bigger than or equal to a. So we're going to break our integration from 0 to infinity into 0 to a, and then a to infinity. And between 0 and a, the function value is 0. And between a and infinity, the function value is 1. Okay, so this term just gives us 0. And this term is the lim as k goes to infinity, integral a to k e to the minus st dt. We've taken the antiderivative of this before. Limit as k goes to infinity of e to the minus st over minus s. Put in the two limits, k and a. Limit as k goes to infinity, e to the minus sk over s, plus this time e to the minus sa over minus s subtracted, which is e to the minus sa over s plus. Okay, when s is bigger than 0, this thing goes to 0 as previously. So when we're done, our Laplace transform is that ua of t transforms to e to the minus sa over s. And again, this is when s is bigger than 0. Okay, let's do one more example. F of t equals t. The Laplace transform of t is the integral from 0 to infinity of t e to the minus st dt, which is going to be the limit as k goes to infinity, integral 0 to k, t e to the minus st dt. Now, this integrand is trickier. We're going to have to do it by parts. So, if you recall, the way we do this is you pick a u part, you pick a dv part, and the right choice here is u equals t. What's left is dv. So you differentiate u, and you get du is dt. You integrate v, dv, and we've done this already today. And what you get is e to the minus st over minus s. Now, if you remember what the formula says, it says this integral is equal to uv, which is this, between 0 and k, minus the integral of v du. Okay, and now that's just this term, and minus minus is plus, and we've found antiderivatives at e to the minus st any number of times already. It's e to the minus st over minus s. There's already an s here, so you get e to the minus st over minus s squared. Again, both of these are between 0 and k. You plug in a 0 here, and you get 0. So from this term, you get a minus k, e to the minus sk over s. Here's that 0. And from this term, you get e to the minus sk over minus s squared. And this 0 term now gives you 0 over minus s squared subtracted 1 over s squared. Now, as previously, these two limits go to 0 for s bigger than 0. And here, the point here is that when s is bigger than 0, this is a negative exponential. That's a polynomial. Negative exponentials overpower polynomials, so this limit is 0. If you don't believe that, you can go back and do a L'Hopital's rule sort of a deal. This limit is 0. We've already seen that this limit is 0, as long as s is bigger than 0. And that means that our Laplace transform for t is just the one term that's left, which is this 1 over s squared, and it's true for s bigger than 0. Let's have a look at our current dictionary. Our translation of functions of t into functions of s. So we know that 1 translates to 1 over s for s bigger than 0. T translates to 1 over s squared for s bigger than 0. E to the at translates to 1 over s minus a for s greater than a. And ua of t, the unit step function, translates to e to the minus sa over s when s is bigger than 0. And this last entry tells us that a linear combination of functions over here in the t language translates to that same linear combination, but of the translates of F and G into S language. And what we'll do in the future is build this dictionary and then start figuring out how to use it to move from T language to S language and from S language back to T language.